Okay, let's continue the discussion of the topology of CG omega. As we mentioned last time, we are going to show that the topology of the CG omega does not depend on the choice of that number 1/2. Remember, the metric does depend on the selection of 1/2. So it's a lemma 1.7. Let the metric rho be defined as in 1.4, just that formula. I will recall it. If epsilon is greater than 0, given, then there is a delta greater than 0 and a compact set K in G such that for F and G in CG omega, the supremum of the distance FZGZ, here Z in K, the supremum is less than delta. This will imply the distance rho FG is less than epsilon. Okay, if they are close enough, then it will be, the distance will be small enough. And this is a one direction. Conversely, if delta greater than 0 and a compact set K are given, there is an epsilon greater than 0 such that for F and G in CG omega, the metric, the distance between FG less than epsilon, it will imply the supremum of the distances, the distance FZGZ, Z in K is less than delta. Less than delta. Okay, so technically you can see that this and this will be an equivalent statement about the closeness, how close two functions are. Okay, so this means the two functions are very close, measured by K and delta. This is another measurement measured by rho and epsilon, right? Measured by rho and epsilon. Okay, so here you do not see the number 1/2. In this part, you do not K compact set K delta, you don't see 1/2. And this place, the rho depends on 1/2. So that's what I say. The topology does not depend on the selection of a 1/2. You can choose 1/2, 1/3, 1/4, whatever smaller number that will work. Okay. Proof. Let's prove it. First of all, this is the definition of a rho FG, like the definition in 1.4. Here we still use 1/2. We still use 1/2. Okay. So we prove one by one. We first prove the statement and then we prove the converse statement. So if epsilon greater than 0 is given. Okay. So we know that this series is equal to 1, converges. A convergent series has a controlled tail. Then for the epsilon, there is a positive integer p such that the tail n from p plus 1 to infinity 1/2 to nth power, it is less than 1/2 epsilon. It will be dominated by this epsilon. This quantity 1/2 is just for the future quantity, future purpose. Here you don't know what partial fraction you use. Later you will see how we use this 1/2. Okay, you have this p. This p is determined by this convergent series. Then you see, for epsilon, we need a compact set, we need the delta. We just choose this compact set as Kp. This Kp is from the construction that G is a union of a Kn. Okay. Okay, now let's see. We choose a delta greater than 0 such that for t between 0 and the delta, including 0, excluding delta, this condition gives t over 1 plus t less than 1/2. This function is an increasing function. When t is 0, it approaches 0. When t is infinite, it approaches 1. When t is close to 0, it can be as small as possible. Okay, so that's why here we choose a sufficiently small delta depending on this epsilon. The delta also depends on epsilon, k depends on epsilon. So that this quantity, this ratio is less than 1/2 epsilon if t is controlled by delta. Okay, so in fact we can solve it. T over plus t is equal to, let's say, L. So t is L plus LT. T is L 1 minus L. Okay, so when t is less than this number, it will be less than L. Right? It's an increasing function. When t is less than this quantity, L is epsilon. Epsilon 1 minus epsilon. When t is less than it, this delta can be selected as this quantity. Okay, anyway, you figure it out. Okay, so we determine k and we determine delta. Let's prove how we get the supremum imply the rho less than epsilon. Okay, so given f and g in Cj omega, satisfying this condition, the supremum of distance fzgz z in k less than delta. This is the condition. Okay. Now let's try to compute the rho fg. Rho fg by definition is a sigma n from 1 to infinity 1/2 to nth power rho n fg 1 plus rho n fg. All right. We're going to break this series into two parts. One is from 1 to p. The other part is from p plus 1 to infinity. Okay, so far it's just equality. And then we know this part is less than 1. So we replace it by 1, then we get inequality. Let's do it step by step. We just replace it by 1, so you don't see this part. It's less than or equal to. And this is a 1/2 epsilon. In the previous part, you see this n is less than or equal to p here. In the first part, n is less than or equal to p. So we know that the kn is always containing kp, which is k. Then the supremum, so the rho nfg is going to be less than or equal to rho pfg, because you have the largest, in this part you have the largest domain kp. So the supremum is an increasing function when you extend the domain. So rho nfg is less than or equal to rho pfg for n less than or equal to p. And the rho pfg, rho p, where is the rho p? Where is the definition of p? Yes. Here, yes. Rho p, this is rho p. Rho pfg is less than delta. So here, this we use rho pfg. Yes, I should write it here. Rho pfg, this is definition is exactly rho pfg. Rho pfg is less than delta. So we have all of them. This is t. T is between 0 and the delta. Then by this condition, so we get less than or equal to sigma n from 1 to p, 1/2 to n. And this part is going to be less than 1/2 epsilon. 1/2 epsilon. Sorry, this is 1/2 epsilon directly. Yes, I don't need to copy it. This is less than 1/2 epsilon by the definition of a p. See, it's less than 1/2 epsilon exactly. Okay, then you factor out this and move this forward. Then this sigma is less than or equal to 1. When it is from 1 to p, it's exactly less than 1. That's epsilon. Okay, so we know that this sigma is 1. So that's a purpose. That's another weak reason why we choose 1/2, because 1/2 is either. The sum is 1. Okay, so we do have the proof from k delta to epsilon. So how do we get k? We determine p. How do we get p? We use this convergent series. How do we get delta? We choose a delta so that the t over 1 plus t satisfy this condition. All right? And the assumption is used this place. Rho p fg is less than delta, and it controls all the preceding distances. Okay, so this is a very, very interesting but not difficult proof for the half of the lemma. Okay, so we proved the first half. Now let's prove the converse statement. Converse statement, remember that yes, you can read it. Converse statement, for delta and compact k, you can find the epsilon so that this distance is less than epsilon, then the supremum for k delta will be, the condition is satisfied. And in the previous proof, we directly choose kp. Okay, we choose k to be kp because here just say there exists k. That's enough. But here in the converse statement, you have to prove it for arbitrary k, not the k1, k2, k3 part. Arbitrary k. All right. Okay, converse. Conversely, suppose k and suppose k and delta are given. We have k and delta. We know that G is the union of a kn, n from 1 to infinity. G is also the union of interior part of a kn, n from 1 to infinity. And k is contained, totally contained in one of a kn. Let's say saying k is contained in kp. Let's use p for some p. For some integer p. Okay. Okay. So we have kp here. Now we have what? We have the supremum of the distance between fz and gz, z in k, it is less than or equal to rho p of fg, because rho p is this supremum but over kp. Here k is less than kp, so we have this condition. Okay. Yeah. So okay, now let epsilon greater than 0 be chosen, so that S is going to be less than or equal to 2p epsilon. When S is less than this quantity, it implies S over 1 minus S is less than delta. Okay, so how do we get this quantity? How do we get S over 1 minus S? How do we get it? If you check here, you will see this is actually the relation between delta and epsilon. Delta is epsilon over 1 minus epsilon. So you see, that's exactly this expression. So that's another, I mean, this is from another viewpoint. You see that you have to really work it out and see what is the relation between delta and epsilon. Okay, so delta should be less than epsilon like this. Then epsilon should be epsilon should be less than delta like this. So you have to be small enough in order to get the desired property. Okay. Okay. So when this quantity is sufficiently small, that you have this S over 1 minus S less than delta. Okay. In this case, we have from here we have T over 1 plus T is less than 2p of epsilon. This quantity will implies T less than delta. This is T. This is T, this is S. You see? This one, T is S over 1 minus S. Then S is T over 1 plus T. You just put this one in this place. All right? Okay, so if rho of Fg, which is sigma n from 1 to infinity, 1/2 to nth power rho n Fg, 1 plus rho n Fg is less than epsilon. If this is less than epsilon, then the rho p of fg over 1 plus rho p of fg is going to be less than 2p over epsilon. How? Why? What's going on? It's because this is a positive series. Positive series is sum is less than epsilon. So each of them is going to be less than epsilon. Actually, here it's not just for p, for everyone. For row 1, row 2, row 3, for row whatever, it's going to be less than 2p epsilon. Okay, so from here to here, it's a very, you start from a very strong condition, you get a very weak condition, and that's the reason we put 2p's power. Okay? Okay, then this gives what? So when this is less than it, you will get t rho pfg. This is t less than delta. T less than delta. But t is a rho pfg, and this is exactly here. This is what we need to prove. Right? You see? It's exactly what we need to prove. And the subtle thing is this 2p times epsilon. If you do not put 2p, the number will be ugly. But with this 2p, it will be perfect. But your epsilon should be sufficiently small, very tiny. All right? Okay, so we do prove that the topology over CG omega does not depend on the selection of a 1/2 if you define your row like in that form. Okay, so for whatever 1/2, 1/3, 3/4, 4/5, whatever smaller positive number can give you the same topology. Okay, so we finish the proof. Okay, so after this theorem, after this lemma, even though it is a lemma, it's a very good practice. Try to do it. It is a good example to appear in exam. Okay, so after this, let's see a two statement. A set O in CG omega with a metric row. Okay, we'll emphasize this metric row. This is open if and only if for each f in omega there is a compact set K and a delta greater than 0 such that the set of functions f so that fz, the distance between fz gz less than delta for all z in K. This is actually an open disk neighborhood. This neighborhood is totally containing O. So every point f is an interior point, has open neighborhood containing this set, then it is open set. Correct? So it's a trivial stuff. Not trivial. Based on the previous proof, it becomes trivial. But the statement will look very weird. B, a sequence Fn in CG omega rho converges if and only if Fn converges to F uniformly on all compact subsets of G. All the compact subset of G, the Fn converges to F uniformly, then the sequence will converge to F in this metric in the function space. Okay. Okay, now let's see the proof. Hey, if O is open and F belongs to O, belongs to this set, then for any then there is, not for any, there is a epsilon n epsilon greater than 0 such that the set G, so that the metric rho Fg less than epsilon open disk, so which is a ball centered at F with radius epsilon. This is totally containing O. That's a definition of open set. And by the part 1 of the lemma, there is a delta and a compact set K such that supremum of what? Distance FZGZ less than delta. So no, here. Z in K. It is less than delta. This will imply the rho Fg less than epsilon. Right? So what do we have? So we have this the set G supremum distance FZGZ Z in K is less than delta. This type of function, it is inside the ball and ball it is containing O. Okay, so that's a one direction. When you have an open set, you definitely have this conclusion. It's done by the part 1. And conversely, if rho has the property that for F in O there is a compact set K and delta greater than 0 such that the supremum, the set supremum of distance FZGZ less than delta Z in K is containing O. Then by part 2, Remember, when you have a compact set K and delta, there is an epsilon greater than 0, such that rho fg less than epsilon. It will imply the supremum of distance fz gz z in k less than delta. So the set ball centered at f with radius epsilon is contained in this set is containing O. So O is open. All right, very cool. So we do prove that for this part you have the open set. Every point has an open disk contained in the set, then it is open set. All right. Okay, so now let's see the part B. Part B, it says in the book, it says the proof of part B will be left to the reader. Well, let's try. Let's try. See if I can do it quickly. So Fn converges to F in Cg omega rho. What does this mean? This means for any epsilon greater than 0, there exists n such that for all n greater than or equal to capital N, the distance between Fn and F is less than epsilon. That's a definition of a convergence, right? Sequential convergence, sequential convergence. Okay, then you see here, we want to prove that it converges on all compact subsets. All compact subsets. Okay, so how do we prove for all compact subsets? There is, for epsilon, by part 1, by the part 1, there is a compact subset K, which is Kp, and what? And the delta greater than 0, such that whenever you have the supremum distance fz gz z in Kp less than delta, it will imply the rho Fn less epsilon. No, we don't need, no, it's not this way. It's not this way, my bad. It's the other way. Okay, so what is the other way? The by part 2. Let's see, by the part 2. Okay, part 2. Okay, we are going to show that for all compact subset, the Fn converges to F uniformly. We want to show that. Okay. We want to show that Fn converges uniformly to F on all compact subsets of G. So it means for any compact subsets subset K of G, and any delta greater than 0, we show the supremum of this uniformly converges to it. There is an capital N such that for all n greater than or equal to capital N, uniform supremum of distance of fnz fz z in this K is going to be less than delta. This is a uniform convergence. If you just get a single point, it's a pointwise convergence. This is uniform convergence. We want to prove this. And for this K and the delta, by part 2, now it's by part 2. By the part 2, there is an epsilon greater than 0 such that whenever rho of f is less than epsilon, it will imply this supremum fnz f z in K is less than delta. Okay? Okay, so let me see. Okay. Okay, so here is the order. So first, okay, now we can see it. First, for arbitrary compact set K and delta, you determine an epsilon such that whenever two elements is less than delta, you get this. But how do you get this rho fnf less than delta? So this place, we introduce capital N. This capital N here. For this epsilon, you see, you have K, you have delta, and then you have epsilon. For this epsilon, you can find, for this epsilon greater than 0, one can find an integer n. There is an integer n. Such that for n greater than or equal to capital N, rho fnf is less than epsilon. Okay? Do you see it? Let me say. So you have K delta first. Then you imply the epsilon greater than 0. There exists epsilon greater than 0 with the property. With this property. This is uniform convergence. And here, how do you get this? How do you satisfy this condition? For this epsilon greater than 0, there exists integer n such that for all n greater than or equal to capital N, rho fn less than epsilon. So that's why you get here. And this is satisfied only when little n is greater than or equal to capital N. So that's the order. You try to solve the other part. Okay, so you try to solve the other part. From the uniform convergence over all compact subset, you get the convergence in the metric form. Okay, so you first write the condition, and second you write what you want to prove. This is not necessary. Okay, so first write condition. This is condition. Then you write what you need to prove and put them together. And you need to use part A or part B. It depends on which direction you choose. All right? Okay, so I just do half of the proof. You can finish the other half, the other direction. Okay, so after this, we have the next one, corollary. So you see here, we just use the lemma 1.7 to show that the topology does not depend on the selection of that smaller number, 1/2. But still, this whole construction depends on your selection of a Kn, compact subset. We want to know if we change that construction, we have this collection of a compact Kn. We may have another collection of compact Kn. Will you still have the same topology? Okay, this is the corollary 1.11. The collection of open sets is independent of the choice of the sets Kn. That is, if G is the union of a Kn and from 1 to infinity, Kn prime, where another set where each Kn prime is compact, satisfy the same property, compact, and Kn prime is contained in the interior part of a Kn plus 1 prime, and if mu is the metric defined by the sets Kn prime, then a set is open in Cg omega rho if and only if it is open in Cg omega mu. Okay, so these two topology, I'm talking about topology, open sets as a topology. Okay, these two topology does not depend on the choice of a compact set. How? The topology convergence, divergence, or the topology open closed, it can be defined by the open. It can also be defined by the closeness. Okay, so if we can confirm a set is closed if and only if it is closed in the other part, then you will get it. You will get the same topology, right? So what do I mean? It says this is a direct corollary of the preceding proposition. Preceding proposition. Why we say it is a direct preceding proposition? Because, well, where is it? We even don't need closeness, still use openness. Okay, here, open or not, It only depends on for arbitrary compact set K and delta you have this property. You see in this definition, in this construction, there is no Kn, the construction Kn, right? You don't have construction Kn. This is the regular distance. It does not depend on Kn. So the preceding proposition part A. Actually, you can also argue it with part B. Part B talks about the convergent sequence. Convergent sequence. The limit point. It discusses the limit point, and the limit points will be determined by the closed set. A set is open if and only if its complement is closed. So if the complement contains the limit point in this way in the row metric, it will contain the limit point in the mu metric, because in the second part, you see here the lim converges to F. My bad. The sequence Fn in Cj omega rho converges to F if and only if Fn converges to F uniformly. So you see here, this limit point discussion does not depend on the choice of Kn. So we can determine the closed set by this. Once you determine the closed set, you can determine the open set. Closed, open, they are relative. One set is closed, complement is open. One set is open, complement is closed. So this is another way to discuss this independence of Kn. Okay. So part A is used to directly discuss open set. Part B is used. It is proper for the discussion of closed set. Part A is proper for the discussion of open sets. Okay. Okay, so we do discuss the independence about the construction of Kn and the selection of 1/2. So you can free to use whatever construction and that smaller number to do this argument. They will give you the same topology, again the topology. And the next topic is about the completeness, and it's different from the current. It's different from these stuffs. We will discuss in the next video. Okay, so try to make the proof of part B the other direction. If it uniformly converges, the sequence uniformly converges to F over all compact set, then it converges in Cj omega rho. Try to prove that. Okay, if you have question, we can discuss it. Okay, so we finish this video and we will continue in a different video. Okay, so this is the last page. This page. This one. And this one. Okay, we finished.